Welcome to the second video on electromagnetism. In my previous video, I have explained the first two topics from this part of 2.6 electricity and electromagnetism, which are the interaction of a current carrying wire with a magnetic field. And then the second part, which is a single charge particle moving in a magnetic field and how that interacts with the magnetic field, which produces a magnetic force on it. Now, in this video, I'm going to cover the next two parts, which are a conductor which is moving in a magnetic field and how it interacts with the field. And then finally, the fourth part, which are basically applications of some of these first three topics. For example, DC motors, which is an application of topic one, and generators, which is an application of topic three. So let's start with conductors moving in a magnetic field. So let's now take a conductor and see what happens when we move it through a magnetic field. So we will start with a conductor, and it could be a metal rod or it could be a wire. So I'm going to take a metal rod here, and we want to move it in an external magnetic field. So we'll have some external magnetic field set up by some magnets in this region over here. So let's probably take a magnetic field which is pointing out of the surface, out of the plane. So that's why it's shown as dots. And now we are going to move this conductor in this direction. Okay, so it's not stationary, it's moving at velocity v to the right. Okay, so what makes a conductor special? And it works only with conductor because inside a conductor we have lots of free electrons. That's why conductors allow electricity to flow through it. Now these electrons are free to move, so we are going to start with just focusing on a single electron. So here's my single electron inside the conductor. And as the conductor moves through this magnetic field, so does these free electrons with it. It's also moving in this magnetic field. So if I focus on just the single electron over here, it's a charged particle that is moving in a magnetic field to the left. So what will happen? There will be a Lorentz force acting on this electron. And let's try to figure out which direction will this Lorentz force be. We have seen how to determine the direction of the Lorentz force acting on a charged particle moving in a magnetic field. So we'll have to take our right hand, point our thumb to the right, and then point our other fingers in the direction of the magnetic field, which is out of the paper in this case. And then you will notice that the palm is facing down, which means the force, the Lorentz force on a positive charge will be pointing down. And that means the Lorentz force acting on a negative charge, which is what the electrons have, will be up. So this electron, the one that we are focusing on currently, will have a Lorentz force or a magnetic force pushing it up. And not only this electron, all the free electrons will feel a force that will push these electrons up. So as a result, because these electrons are free to move, what will happen? They will gather at this end of the conductor. So electrons from the rest of the conductor, from this other end of the conductor, will gather at this end. So overall, this end of the conductor, because of this excess electrons at that end, will become negatively charged. And from here, because the electrons have moved to this other end, so we'll have lack of electrons over here or missing electrons from this end, and therefore this end will get an overall positive charge. So that's how this magnetic force will separate the charges inside the conductor and making one end negatively charged. Over here, the top end is negatively charged because of the excess electron gathering over there, and the other end, the bottom end, became positively charged because it has lost electrons. So that's how this charge separation occurs. So a conductor moving through a magnetic field will experience this charge separation. And whenever we have a charge separation like this, then it induces a voltage across the two ends. So if I connect a voltmeter, so for example, if I take a wire and then connect a voltmeter across the two ends of this conductor, here's a voltmeter, then this will show us a voltage. It will show us that there is a voltage across the two ends. And this voltage that is produced due to the charge separation is known as the induced voltage. Okay. And this induced voltage across the ends of a moving conductor in a magnetic field is given by this relationship. The voltage V across the two ends is equals to the strength of the magnetic field it's moving through times the speed at which the conductor is moving times the length of the conductor, again in the magnetic field. Only the length of the conductor that is in the magnetic field will produce this voltage. So use this length over here for the calculation of the voltage, okay, not the full length of the conductor. Okay, so there's another thing that you need to be mindful about when you're calculating this induced voltage, which is this V over here, the velocity. Now, this V that you should be using in this calculation is the voltage, sorry, the velocity, which is perpendicular to the magnetic field. So in the example that I have shown here, it's already the V that I have shown is already perpendicular to to the magnetic field. But if that's not the case, you have to again do the same thing, take the velocity vector, split it up into two components, and then only use the component which is perpendicular to the magnetic field to calculate the induced voltage. And if V is parallel to the magnetic field, or if V, the velocity is anti-parallel to the magnetic field, that means the conductor is either moving in the direction of the magnetic field or in the opposite direction of the magnetic field, then in that case the induced voltage will be zero. There will be no induced voltage. Okay, and so with this, I have covered the three main topics from electromagnetism, the main concepts that you need to learn from this topic. Now, the rest is all application of this into different situations. So I'm going to use some past exam questions and show you how you can apply these concepts, especially this one over here, conductor moving in a magnetic field, to analyze or to solve different problems. Okay, so let's start with one such example. Okay, so what we have here, I have taken this question from 2023 exam paper, and it says the diagram below shows a metal axle that is free to roll on two parallel metal rails. The rails and the axle are in a magnetic field. The ends of the rails are connected to a 120 volts power supply, and they have given you a bunch of information about this situation. So they have given you the strength of the magnetic field over here, that's B, the length of the axle, which is this length from here to here, the distance between the parallel metal rails, so that's this distance over here, the width of the magnetic field, which is this thing over here, and then the total effective resistance of the circuit and the voltage of the power supply. Now, these two parts you will probably need to answer part A and B, which I'm not answering over here. I'm just showing you part C because that's an application of what we have just discussed about a conductor moving in a magnetic field. So for part C, it says the power supply is now removed and the metal axle is given a push so that it is moving to the right as shown in the diagram over here. It's moving in this direction at 3.10 meters per second as shown in the diagram. So we end up with this metal axle, which is basically our conductor that is moving in a magnetic field, and the magnetic field is pointing out of the surface, and they have given us the velocity. What we have to do is clearly mark the negative end of the axle on the diagram. So we have to use our right hand slap rule and point our thumb to the right, because that's the direction of the velocity. Point the rest of the fingers in the direction of B, which is pointing out of the paper, and then you can see the Lorentz force is downwards, which means the positive charges will feel a force downwards, and the free electrons inside the conductor will feel a magnetic force upwards. So the electrons will move in this direction and they will gather over here. So this end, the top end of the axle, will become negatively charged. I mean, they have asked us to mark only the negative end, so this is our negative end. If we also have to mark the positive end, then this will be the positive end of the conductor. Okay. Now, next part is calculate the voltage induced in the axle immediately after it is set moving. So then we have to use the formula V is equals to B V L, and everything is given. B is given, so we can substitute that 8.10 times 10 to the power of negative 3. V is given as well, that is 3.10 meters per second. And then we have L, and be careful about this L. The L that we have to use is the length of the conductor in the magnetic field. So it will be the length of the axle, which is 0.950. So if you multiply these three quantities, then you will get the voltage. So it's equals to 0.0239 volts. Okay, so the next part of the question says, with the power supply still disconnected, a wire is connected between the rails and the axle is given a push so that it is moving to the right at 3.10 meters per second. So you can see over here, this end, the two ends of the rails are connected with a wire. So what it does is basically it makes a closed circuit now. So you have this axle which is moving in the magnetic field, and because of that, we just calculated that there will be a voltage, there will be charge separation between the two ends, and that will induce a voltage across the two ends of this rail. And as a result, if you provide a closed circuit, if you make a closed circuit, and this part is producing a voltage, then it will set up a current or allow a current to flow in the circuit. This induced voltage V will produce a current I, which you can work out by using Ohm's law. I is equals to V over R. This V will be the voltage we calculated earlier, and R is the resistance of this closed circuit. Okay, so as a result, what will happen, the electrons, because they're pushed upwards, they will continue to move in this direction. So this is how the electrons will keep moving in the circuit, and it will basically set up a current in the opposite direction. And we know current flows from positive end to the negative end of a battery. So there will be a current flowing in this direction through the circuit. So now we end up with a conductor here with a current I in a magnetic field. And we have seen earlier what happens if you have a conductor with a current. So if you have a current carrying conductor in a magnetic field, then there is another magnetic force, another Lorentz force that acts on this current carrying wire. And if you apply the right hand slap rule, point your thumb in the direction of the current, which is downwards, and then point your fingers in the direction of magnetic field, which is out of the plane, out of the surface. Then you will notice that the palm is facing to the left. So this current carrying wire, because it's in a magnetic field, will feel a Lorentz force, a magnetic force to the left. So it will be pushed to the left. It's moving to the right, and because of that movement, it's inducing a voltage. Because of that voltage, there is a current in the circuit and through the conductor, through the axle, and because of that current, you have a current carrying wire in a magnetic field, and that causes this Lorentz force acting on a current carrying wire. So you can see this force is basically in opposite direction to the velocity. So what it will do is it will not allow the axle to move at constant velocity, but it will decelerate it, it will slow it down, and that's the effect of this current in the wire. Okay, so the question asks you to describe the motion of the axle after it is set moving, and this is how you describe the motion. The next application I'm going to show you is through this 2020 NCEA exam question. Now, what we have here is a plane with metal wings that has one wing tip painted blue, other wing tip painted red, and the wingspan is 68.4 meters. The plane is flying horizontally at this speed, and they have given you the speed in kilometers per hour, but in bracket they have also given it to you in meters per second, which is the one we have to use for calculation. And it's in a region where Earth's magnetic field is vertical and has a strength of 40 microtesla. And again, the number given in the bracket is the one that is in Tesla, and that's the one we have to use for any calculation. And they have shown you the diagram, so you can see the magnetic field is pointing into the surface. We have to show that the induced voltage between the ends of the wings is this. It's an easy question. You just have to use the formula V is equals to B VL, and I'm sure you can all do that. I want to go through the next part of the question quickly because that's the one where I want to explain a few. There might be some confusion about some of the points over here. So we have to complete the following table. Assume each change is made to the original plane separately. So what is the change? Speed of the plane increases, and we have to describe the effect on the size of the induced voltage. So we can see from this relationship, the induced voltage is proportional to the speed. So if the speed increases, then induced voltage V will also increase. Okay. And which color wingtip is positive? If the speed increases, the voltage, induced voltage will increase, but whichever tip was positive, it will still remain positive. So I think in this case, it will be the red tip, which is positive. So the red tip will still be positive. Okay, it doesn't change the tip that was positive. So next point is plane is flown in the opposite direction at the same speed. So now instead of flying this way, the plane is now flying in the opposite direction. So that's the direction of the new velocity. And if that happens, then it's moving at the same speed. So V in this formula still remains the same, which means the induced voltage, which depends on the size of the velocity, that means the speed and not on the direction, will still be the same. So induced voltage V is same as before, but or as original, and the what will change is the tip that is now positively charged. So now the blue tip will become positively charged. Okay. And then finally, if the plane climbs vertically upwards from the earth, so velocity is upwards, which means it's out of the surface, and magnetic field is into the surface. So this is a situation where V velocity is actually anti-parallel to the magnetic field, and I have explained it to you earlier. If the object is moving in the direction of the magnetic field or in the opposite direction, then there is no induced voltage. So induced voltage will be 0 volts. Okay, and because there is no induced voltage, so there will be no tip with positive charge. Okay, because there will be no charge separation. There's no magnetic force acting on the free electrons inside the conductor, and therefore there will be no induced voltage, and no tip is positive, no tip is negative. Okay, so that's this part over here. That's the part that I wanted to explain. Now the next part of this question is also quite important. So what happens is, I want to mainly go through part D. We have an engineer who designs the speed warning device that consists of a wire connecting the wingtips and a zero point 0.5 volts lamp. So let me just zoom this in a little bit. So now what the engineer has done is connected the red tip with the blue tip with a wire, and there is a there's a lamp connected in that wire. Okay. The engineer states that the faster the plane goes, the brighter the lamp will glow. Use physics principles to explain and justify if and how this arrangement would work as a speed warning device. Okay. Now, what will happen in this situation? It's not just the plane's wing that is moving in the magnetic field. So, the wings of the plane is one conductor. So, this part over here, the wings of the plane is one conductor that is moving through the magnetic field, and that conductor will induce a voltage V across the two ends of the tip, and that will be equals to BVL, which depends on how fast this is moving and the length from the red tip to the blue tip. And there's a second conductor, which is the conductor that connects the two tips, and there is a lamp in that wire. Okay, so this conductor is also moving in this magnetic field with the exact same speed. So that will also induce the exact same voltage across the two ends of this wire. And these two voltages will basically try to set up a current in the circuit in opposite direction. So they are like two batteries. So it's like one battery connected like this to another battery, which is also connected like that. So the positive, this battery has a positive end over here, negative end over here. The second battery also has a positive end over here and a negative end over here, and the voltage induced, or the voltage of both batteries, are same. So what that will do is they will cancel each other's effect. They will not let any current flow in the circuit, because this battery here will try to set up a current in this direction, and then this other battery here, or the other second induced voltage, will try to set up a current in this direction. So they will basically cancel each other's effect, and we will end up with no net induced voltage, and therefore no current in the circuit, and therefore the lamp will not glow. So if instead of a single conductor, if you have two conductors like this, and they are both moving together in that same magnetic field in the same direction, then overall the induced voltage in the two conductors basically cancel each other out, and we end up with no current in the circuit, or no overall induced voltage. So this arrangement as a speed warning device is not going to work. Now, the last two applications that I'm going to discuss here is our motors and generators. And these are applications of all three topics. In fact, the first topic, current carrying wire in a magnetic field, and a conductor moving in a magnetic field. So these are applications of these two topics, and these are really important applications that you need to understand. And so what I have done over here is again taken a past exam paper, past exam question, which is about both motors and generators, and I'll use these to explain how motors work and how it's an application of a current carrying wire placed in a magnetic field, and then do the same for generators. So here in the question, it tells us that the diagram shows a simple electric motor. So it shows you the configuration of an electric motor. The direction of the conventional current through the wires is shown by the arrows. and we have to calculate the value of the force on side AB. So let me first explain the basic configuration of a motor. We know a motor is a device which allows something to spin, and to make a motor, what we need is some magnets. As you can see, you have a north pole of a magnet and a south pole of a magnet, and that sets up a magnetic field in the area between the magnets, and the magnetic field will be pointing to the right from the north pole to the south pole. Okay. And then additionally, we have a current carrying loop. So you can see we have made a loop, A, B, C, D, and it's connected to battery. So this end is connected to the positive terminal of the battery. This end is connected to the negative terminal of the battery. And therefore, we have a current through this conducting loop starting from here in the AB section of this loop. This is the A and B part. The current is flowing in this direction. Then in the BC part, the current is parallel to the magnetic field. For the CD part, the current is in this direction. And then if you focus on the on this section, this tiny section over here, and this section over here, the current is in this direction, which is anti-parallel to the magnetic field. Okay. Now, first part of the question, it asks us to calculate the value of the force on side AB. So it's basically a current carrying wire placed in a magnetic field. You can use the relationship force, magnetic force is equals to B I L. I think all the values will be provided to you. You just have to substitute the magnetic field strength, the current, and the length of the wire, and then you can work out this force over here. But I'm more interested on the second part of the question. It says for each part of the wire, state the direction of the force as either left, right, up, down, out of the page, into the page, and no force. So first is direction of force on AB. So we have this AB wire carrying current, and it's placed in a magnetic field, and then we can use right hand slap rule to work out the direction of the Lorentz force or the magnetic force acting on this wire. So if you point our thumb up, because that's the direction of the current, and then point the rest of the fingers to the right, because that's the direction of the magnetic field, you will notice that the palm is facing down, which means this wire will be pushed downwards. To show that in here in the diagram, I have to draw a vector which is pointing away from me down into the surface. Then I will draw it as a cross. So this is the direction of the magnetic force on the wire AB. And here we can write direction of force on AB is into the page. Okay. And then the direction of force on BC will be 0, because as you can see, the current through wire BC is parallel to the magnetic field, and we have discussed it earlier that if these two are parallel or anti-parallel, then there will be no magnetic force. So then for BC part, there is no force. And similarly for the DA part, there will be no force either. And direction of force on CD will be just opposite of AB, because if you check the direction of the current through CD, it's exactly opposite to the direction of current through AB. Therefore, the direction of the Lorentz force will be opposite as well. So it will be out of the page. And if I show that in the diagram, I will show it with a dot, because force pointing out of the paper, out of the surface, will be shown as a dot. Okay. So you can see that these two wires, AB and CD, they have forces acting in the opposite direction. One is being pushed down into the page, and the other wire is being pushed up out of the page. So if this loop, this conducting loop, is free to rotate, then what will happen is it will start rotating like this, okay, around this axis. So it will start spinning around this axis. And that's how motors work. So we use current carrying wire, current carrying loop, in fact, placed in a magnetic field, and that allows it to spin because the magnetic force allows it to spin around an axis going through the center. So if you have some blades, for example, some blades attached over here, then those blades will start spinning. Okay. Later, what you can consider is what will happen once it has rotated half a cycle. So that means after half a rotation, the CD wire will end up over here and the AB wire will end up over here. So the CD and the AB wire will swap position, and then what that will do is if we keep the AB and CD wire connected to the battery the exact same way as it's connected now, meaning the end A is connected to the positive terminal of the battery and end D is connected to the negative terminal of the battery, then the direction of the current through AB wire and CD wire will remain the same even after they have swapped position. And then what that will do is it will swap the position of the forces as well. So what I mean is, in this new situation, what will happen is after half a rotation, let me just try to draw it again, half a rotation, this will become AB because AB will move over there, and this will become, sorry, not like this. This is A and this is B and this is C and this is D. Okay. So if we keep the connection exactly as it was before, that means A is still connected to the positive terminal and D is connected to the negative terminal. Now the current will flow like this. So then on the AB wire, the force will be into the page as before, and on the CD wire, the force will be out of the page as before. So now it will start rotating in the opposite direction. So previously it was rotating like this, but now it will rotate like this. So that's not very helpful because then the motor will rotate in one direction for half a cycle and then it will rotate in the opposite direction for the other half of the cycle. So to keep it spinning in the same direction, what we need to do is we have to swap the connection to the battery. So instead of keeping the connection as it was originally, we have to make the end D connected to the positive terminal and end A connected to the negative terminal, and that will reverse the direction of the currents through the wire. So over here the current will still be in this direction and over here the current will in this direction, and that will keep the direction of the forces the same as before. So this will be into the page and this will be out of the page, and it will keep spinning in the same direction as before. So that's how a motor. All right, so now the third part C of this question shows us how a generator, a simple generator works. And it says the diagram shows a simple generator. The coil contains 60 turns of wire and is rotated clockwise. And that actually describes how a generator works. So you need to take some conducting wire and make loops with it. So this one over here, this A, B, C, D loop is made of wire which is coiled around 60 times to make 60 turns. And then you have to physically rotate this loop in a magnetic field. So this loop here is rotating about this axis. So you have to have a mechanical process to move these conductors, specifically this A, B and the CD conductor in a magnetic field. And as you can see over here, these two north poles and the south poles are generating a magnetic field pointing this way from north to south. So this is just an application of a conductor being moved in a magnetic field. And of course, we have seen earlier, if we do that, then it induces a voltage. And that's exactly what the question is asking you to do over here. It's asking you to calculate the value of the induced voltage in the coil when the wire AB is cutting the field at 6.2 meters per second. So we are given the velocity v at which the AB wire is moving, and we have to calculate the induced voltage V. So we know voltage V is calculated using this relationship BVL, and everything is given. You have to use the magnetic field strength given over here. So it's 4.7 times 10 to the power of -3 times V, which is 6.2, and times L. And over here we know the length of AB wire is 5 centimeter, but we should change it to meters first. So this will be 0.05 meters divided by 100. So that is 0.05. But there's one more thing we have to do here, because there are 60 turns. So I think what we need to do is we have to multiply this by 60, because over here we not only have a single wire, but we have 60 of these wires, and each will have an induced voltage in it. So overall the total induced voltage will be times 60. We also have to multiply this by 2, because it says calculate the value of the induced voltage in the coil, which means there will be this amount of induced voltage in AB, and then there will be equal amount of voltage in CD as well. So overall the total induced voltage will be these two combined. So what we need to do is actually multiply this by 2 to include the induced voltage of the CD part as well, and then that is the total induced voltage in the entire coil. Okay, so that's this part over here. Now for part D, it says the diagram shows the coil in the generator being rotated clockwise, and because of this rotation we are actually continuously moving these conductors in a magnetic field, and that's how we are generating voltage. That's the basic principle of generating electricity or voltage by moving a conductor in a magnetic field, and that is exactly what a generator does. Okay, so over here, it's this diagram shows us the different positions of the loop. So here you can see position A is showing the loop in a horizontal or a flat position, then position B where it's vertical, and then it keeps turning, and then again it's horizontal, and then again it's vertical. So this shows the position of the loop over one full cycle, starting from here, getting vertical, then horizontal again, and then vertical. So that's one full rotation of the loop in the magnetic field. It says in which position of the 4 positions labeled A to D above would the largest voltage be generated and no voltage be generated. Okay, so for that, what you need to understand is in position A, this AB section of the wire is moving in this direction. So that's the direction of the velocity of the AB wire, because it's going in a circular motion, kind of like this. It's moving in a circle, and we know that in circular motion, the velocity is always tangent to the circle. So at this position, velocity of AB is this way, velocity of CD is this way. Okay, and the magnetic field is in this direction from north to south. So you can see the velocity and magnetic field, they are perpendicular to each other, and the velocity and the induced voltage here V is equals to BVL. And remember how we have to use V, which is perpendicular to B, then we get the induced voltage. And because here entire velocity is perpendicular to the magnetic field, therefore we can use all of that V to calculate the induced voltage in position A. In position B, however, if you consider the velocity of AB wire, it's in this direction because it's going in a circular motion it's following a circular path like this. Okay, so over here the velocity is tangent to the circular track and it's in this direction, which is in fact parallel to the magnetic field. So velocity and magnetic field are parallel to each other, therefore velocity will have no component perpendicular to the magnetic field, and the induced voltage here will be zero. There will be no induced voltage in position B. Position C, same process, it will have maximum induced voltage because all of the velocity is perpendicular to the magnetic field. Position D, induced voltage is zero again. Okay, because here if you consider this AB part, because that's where the AB part is now, velocity is anti-parallel. Velocity is in this direction, which is anti-parallel to the magnetic field. So again, the induced voltage will be zero here. Okay, so in which position or positions of the four labeled A to D above would the largest voltage be generated? So largest voltage will be generated in position A and C, and no voltage generated in position B and D. Okay, and use physics principles to explain your answer to the previous part of the question. I have already explained why we have maximum voltage over here, because all of the velocity is actually perpendicular to the magnetic field. So that's why we get the maximum induced voltage, and over here none of the velocity is perpendicular to the magnetic field. It's in fact parallel or anti-parallel, and therefore no induced voltage. In any other position in between, so for example, if the loop is kind of rotated, but it's like this. Okay, so it's kind of at an angle like that. So it's not fully flat or not fully vertical, but it's kind of at an angle. Then the velocity will also be at an angle like this to the magnetic field. The magnetic field is this way. The velocity is tangent to the circle because it's the circular track. So it will be at an angle. And in that case, you will have a component of the velocity which is perpendicular to the magnetic field and a component which is parallel to the magnetic field. So this component is what we will have to use to calculate the induced voltage. And as you can see, because it's a component, it's a part of the entire velocity, it will be smaller than the total velocity, than the actual velocity. So therefore you will get less voltage induced in that position. Okay, and then the last part, clearly indicate on each appropriate diagram the direction of any electron movement caused by charge separation when coil rotates. So over here you will have to use your right hand rule to work out which direction the electrons will be pushed, and therefore determine which direction the electrons will be moved because of the magnetic force. I think you guys can do that. So I guess that explains all the different examples that I wanted to go over. So what I'm going to do is finish the video over here, and I hope that was useful. So see you guys again next time.